Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. In a lot of math classes, one of the focuses is on reasoning. So a lot of the things that your teacher's asking you to do is not because they don't know the answer, but it's because they're wanting to help your brain learn how to think. So in inductive reasoning, that's exactly what we're doing is we're just trying to learn how to think and justify why something is happening, because that is something that translates to the real world. Say you're a contractor trying to make a bid for somebody's project. You're going to have to justify your cost and you're going to have to reason that out for them. So that's one of the reasons why this is a big goal in high school. And you'll see that in proofs and other types of reasoning practice in geometry. So here we're going to make conclusions based off of patterns that we see. So let me say that I'm going to just go with 800, 400, 200, 100. Dot, dot, dot. So that dot, dot, dot tells me that this pattern is going to continue. So we need to make a conjecture, which is an educated guess, basically, about what the next, we'll just go with the next two numbers in the pattern. Did you pick up something that's going on? If you said that they cut it in half, meaning they divided by 2 or multiplied by 1/2 each time, you'd be absolutely correct. That is the pattern going on here. And therefore, we could make a conjecture or a hypothesis that the next number in the pattern is going to be 50 and the next number after that's going to be 25. So again, it's not proven, but it is, that's why it's a conjecture. We can't prove it. I mean, checking the answer key in the book just means that we've thought the same way as the person who wrote the problem. But we have it for inductive reasoning. They make conjectures all the time in science. They make a hypothesis and then they try to prove it. Not always are they able to prove it. Sometimes time just has to go on to see if that happens. They'll do it with populations. We think the population is going to do this, but there's a lot of factors, so sometimes their conjecture is correct, sometimes it's not. Okay, so just so we understand some terminology, our first term was the number 800. Our second term was the number 400. Our third term was the number 200. Our fourth term was the number 100. So the term is like the first blank, the second blank, the third blank, the fourth blank. The number itself is what's actually there. Okay, so I'm going to give you 4 terms and then I'm going to ask you to make a conjecture. And I'm going to color code so you can tell the difference. So this time, instead of giving you numbers, I'm going to give you an image. So here's term number 1. Term number 2. Term number 3. And term number 4. Whew. Well, that was a lot. I want to know, I don't want to draw it, but how many dots? In term 5. And then also term 6. Well, let's make a list. We'll just go term, dots. Term 1 had 1 dot. Term 2 had 5 dots. Term 3 had 11. And term 4 had 19. So what we need to do is we either need to visualize a pattern in the dots or a pattern in the count of the dots. That's up to us. So I'm going to do in the number of dots themselves. I notice that from here to here, we added 4 dots, and I can see it in the picture. Then we added 6 dots. Then we added 8 dots. Do we see a pattern in what we're adding? Absolutely we do. So 5, we would add 10, right? So we'd be at 29. And then we'd add 12. And we'd be at 41. Now I also noticed a pattern in the picture. I noticed that this was 4 by 4 with 3 on top, and 3 is 1 less than 4. This was 3 by 3 with 2 on top, and 2 is 1 less than 3. This is 2 by 2 with 1 on top, and 1 is 1 less. This is 1 by 1 with 0 on top. So 4 minus 1 is 3, 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0. That is also another way that we could see it, is that now we know that we would have to have 5 by 5 with 4 on top, which is 29, or 6 by 6 and 5 on top. Now, the nice thing about this pattern and writing it this way is that I could say it is my term being multiplied by my term plus my term minus 1. And I could actually turn it into an equation so that I wouldn't have to like keep adding all the time. And I can make a conjecture that way with an equation. We don't have to do that though. But we definitely could. So that would be our term squared plus our term minus 1. So looking at it from a plus pattern or looking at it from a equation pattern, either way helps us figure out that there's going to be 29 and 41 respectively in term number 5 and 6. Okay, so we did a numerical pattern, we've done a visual pattern. We can also do percentiles. So let's say you have taken just some stats. So you looked at 4 different voting polls, okay? And you knew that in poll number location 1, there were 3,511 eligible residents. For poll location 2, 3,790 residents. Poll location 3 and poll location 4. Now, the information hasn't come in from poll location number 5, but you know that they have 5,562 residents. Now, these are just the residents, not the voters, not the people who showed up. So we'll go with eligible residents. Okay, now to come out to vote, only 386 votes were cast. In poll location 2, they only had 414 votes. By the way, this happens a lot with smaller elections. If you care about your local stuff, go out, do your voting, make your voice heard. There are elections every year. Talk to your government teacher about that. So voting didn't happen a lot. A lot of people didn't show up. Maybe there was only one thing on the ballot. Who knows? But without getting there, could we make a conjecture about how many voters we think are going to happen? We can if we look at the percent of the population who showed up to vote. Okay, so to find a percent, we're just going to divide. 386 divided by 35.11. That's right around 11%. $414 divided by 37.90. That's right around 11%. 451. That's just a smidge over 11%, but I'd say that's still pretty close to 11%. And let's see if it holds true at voting location number 4. This, yeah, still right around 11%. So it looks like 11% of voters have showed up to location 1, 2, 3, and 4. So can we make a conjecture that 11% is going to show up to location number 5? I think we can. So how many votes out of 5,562 will equal 11%? And percents are technically out of 100, right? Okay, so we have our proportion. Cross product, because we can cross product because there's an equal sign. So 100x equals 6, let's see, 11 times 5562. Just wanted to make sure I was correct. And then when we divide by 100, I don't think we can have a partial person, so I would say approximately 612 voters. So again, we just looked at it as a percentile because we wanted to make a conjecture about how many voters we could probably get in our 5th location. Is that necessarily going to be true? No, but it could be. All right, so you can make these conjectures all day long, but what if you're wrong? How can someone prove you wrong? Well, they can prove you wrong with what's said to be a counterexample, okay? You might have done this to your, parental figures. Okay, they might say, every time you come home late, I'm going to take your phone for a week. And you might go, well, the one time I came home late and you didn't take my phone. Or every time it rains, they canceled the football game. Well, there was that one time it rained, but because there wasn't lightning and it only rained like a sprinkle. There's always those, okay, but, every time you get pulled over, you get a ticket. Well, that one time I was able to talk my way out of it, whatever. Okay, so a counterexample is you showing them that is not true. So what if I said all prime numbers are odd? Okay, reminder, a prime number is something that has exactly 2 factors, one in itself. Okay? Isn't 2 1 times 2? Is there any other way to factor 2 out? So 2 is a counterexample. We can say false. It's not all prime numbers because 2 is a prime number. So we found a counterexample. We proved this statement wrong. So all we have to do to mess up logical reasoning is find a counterexample. So keep in mind that when we make conjectures, those are things that are going to appear to be true until proven false. Okay? So for example, baseball games are canceled when it rains. Okay? So baseball games are canceled when it rains. And I know we can all think of some of those ball games you've watched on TV where they pulled out the tarps to protect the fields, things like that. Okay? Well, did you know that on 8/8 of 24, Yankees versus Angels was played in a very heavy rain. So there you go, 8/8/24, Yankees versus Angels. And I'm sure you can find a lot of more counterexamples, right? Okay. So here's a statement. The rule for odd numbers is 2 times n plus 1 when n is an integer. Okay, remember integers are like numbers that are not decimals or fractions. So, do you think the statement appears to hold up or not? Can you find a counterexample? Well, let's just try. So, integers greater than 0. So, n values. 1, 2, 3, 4, 5, 6. I think 6 should help us. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 1 is 7. Every time I multiply by 2, I'm getting an even number, and then I add 1 to it, and I'm getting an odd number. So does it appear to hold up? Yes. So the statement appears to be true. If you can find a counterexample for it, let me know. But this one appears to be true. And even if I used an integer 0, I would still, if I substituted 0 for n, I think this rule could be expanded. So let's see. Remember, an odd number is one that's not divisible by 2. So let's try if n equals -8. 2 times -8 plus 1, that's -15. I would say that's odd to me. So I think they could have expanded this statement. So remember, a conjecture is something that appears to be true. You can disprove a conjecture by giving a counterexample. And this is just, reasoning, thinking it out, and giving an explanation. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.